Welcome back to this lesson 3 in complex numbers. In this lesson, we learn about the geometrical interpretation of complex numbers. When we say geometrical interpretation, normally in coordinate geometry, we have the x-axis and the y-axis, and then we have the negative x-axis and the negative y-axis, and we say this is the first quadrant, second quadrant, third quadrant, and the fourth quadrant. Now any number here or any point here can be interpreted as in terms of x and y. Say if I take a point here, say point P, let's say this is 3 and let's say this is 2, so we can say this point P is this is 2y, this is 3x, so that is represented by 3x and 2y. So likewise we can have another point here, shall we say there. So shall we say this distance here is -3 and this is positive 2 or say 1.5 or whatever. So we can say this point, shall we say this is Q, can be represented as say 2x minus 3y. So similarly, any point in this quadrant or this quadrant we can interpret within these coordinates x and y. So we have a similar approach in complex numbers. In complex numbers, any complex number can be represented within this what we call the argon diagram. This argon diagram has the same coordinates, but we interpret them differently. This is our real axis and y-axis will be our imaginary axis. So how we get to this point is this. Now this real axis, shall we say this is say positive 1, and 180 degrees opposite we get -1. So in other words, that's the negative real axis. Now let's assume we have a operator what we call the J operator. When we multiply this 1 by a quantity J, it turns this real axis vector, or we call it now the phasor, it turns it by 90 degrees. So when you multiply this vector, say shall we say J, this 1, we multiply it by this operator J, and then it turns it first, it turns it by 90 degrees, and then you multiply it by further J, and then it turns it by 180 degrees, altogether 180 degrees. So when it turns 180 degrees, we see that it's coming to this negative real axis. So if we take 1 and multiply it by J, that is turning the phasor, by 90 degrees. And if you further multiply it by another j, it turns it by 180 degrees. So that turning the phasor by 180 degrees. So now j times j is j squared. So that means when you multiply this 1 by j squared, we see that we are getting negative 1. Right? We are approaching, or we are getting negative 1. So that means j squared is equal to negative 1, and this gives us that j is equal to negative 1 square root. So this is where we actually trying to get at the same time showing of this complex numbers within this argon diagram. The representation of complex numbers by this argon diagram. So now we can show this as the real axis, and that's the imaginary axis, that's the negative real axis, and that's the negative imaginary axis. Now what we said was we have a phasor here. When you multiply that by j, it rotates by 90 degrees, and when you further multiply it by j, it rotates by 180 degrees, and when you further multiply it by that, it comes to another 90 degrees, that is negative imaginary axis, and further multiplication by j, it comes back to this. So we can prove that what we are doing is tallying with this complex number definition of complex number. We define complex number, this j operator, as square root of minus 1. So j squared is minus 1, and j cube is minus j, because j cube is equal to j times j times j. So when you multiply j by j, you get negative 1, and when you multiply that by j, you get negative j. And let's say you multiply this phasor or the vector by j 4 times, that is j to the power 4, that is j times j times j times j. So you will see these two will give us negative 1, and these two will give us another negative 1. So we'll write it within brackets like that, and negative 1 times negative 1 is positive 1, and that is where we have ended up. So when we multiply it by j, we get j axis there, and further multiply it by j, we get to the negative real axis, because j squared is negative 1, and when you further multiply it by that, you get negative j, and when you further multiply by 90 degrees, or multiply by j, which turns 90 degrees again, we get positive 1 and back to the real axis. So we can see that taking this x-axis as the real axis and y-axis as the imaginary axis has justified our what we have assumed or what we have inferred. Now let's take this argon diagram and let's see how we can represent a complex number within this argon diagram. So that's our real axis, that's the j-axis, that's the negative real axis, and that's the negative j-axis. So we'll take any complex number here. We will say that complex number is z, and that is equal to x plus jy. So that's the real part and that's the imaginary part. So let's take that complex number there, that's the z, and that is the real part, which is x, and that's the imaginary part, which is y. So the complex number is represented there like that, and this phasor, the other way of representing this complex number by this phasor z, we say that is this phasor there, which is rotating about the origin. So any complex number similarly can be represented by a phasor or a vector. A phasor, or we say a vector. And if I give another example, let's take a complex number there. Shall we say this is that is b, and that is a. So this complex number, shall we say this is z dash. Z dash can be written as a plus jb. Now a is, shall we say this is negative, so it is negative a plus jb. If we take this value as this magnitude here as a, and then it is because it's a real negative real axis, it becomes negative a, so it will be negative a plus jb. So let's have some real values instead of this x and y. So we will have the real axis again and the imaginary axis, the j there, and negative real axis and negative imaginary axis. Right. So let's take something real values. Okay, we'll have a vector here, and that is say z, and shall we say this is 4 and this is 3. So we can say z is equal to 4 plus j3. Now we are going to define something called the modulus of a complex number. The modulus of a complex number is defined as the magnitude of this phasor, the magnitude of the phasor, and normally we write it like this, right? And that is equal to the magnitude of this vector here, or the phasor here, which is by Pythagoras theorem is the square of this plus square of this and the square root, sum of square root of sum of the square of this and this. So that is 4 squared plus 3 squared square root, because we know this is a right angle triangle, and from Pythagoras theorem it will be 4 squared plus 3 squared square root, which we know that is 16 plus 9 square root, which is equal to 25 square root, which is equal to 5. So the length of this, the magnitude of this, or the modulus of this complex number is 5. And then we will define another quantity here, that is what we call the argument. Argument is the angle here, the angle with the real axis. So argument we write as, say, arg, arg, arg of z is equal to, now this angle we always measure it from the positive real axis, so, and measuring it anticlockwise, and argument z, that is tan inverse 3 by 4, which you can calculate and see what it is. So it is tan inverse 0.75. So from the from calculator we can find out that 0.75 tan inverse, which is 36.86. So that is 36.86 degrees. So in the next lesson, let's do some more modulus and arguments of complex numbers. Thank you.